Okay, so here's some common topologies just to give you a little practice. The top two are really just variants on the ones we just did. And the bottom two are interesting because they sort of teach you that you can not just do voltage to voltage amplification, you can do current to voltage or voltage to current. So take a look at the top one. We'll just give you some quick and dirty guidelines really so you can find the solution. So the solutions are all provided for you. Those are the equations. But if you take a quick look, what does this look like to you, just this part there, Tom?
That looks like your inverting amplifier.
Yeah, it's an inverting amplifier. And if I didn't have RS2 and RS3, oops, that's a typo. If I didn't have these branches, it would be an inverting amplifier. But what we've done is we've added additional branches. And so the thing to notice is this current, call it IS1, and that current, call it IS2, and that current, call it IS3, are all going to sum up and go through, and go through the feedback current.
Oh, and they're summing up just because of KCL at that node.
Yeah,
all those currents have to
KCL
add.
there. And you know that this is 0, just like before, right? And so if you go ahead and do that KCL, and you also remember that V plus equals V minus, and that equals ground, right, in this particular amplifier, you can do the KCL just like we did before, except now you'll have 3 additional branches. And when you're done, you'll find that each branch contributes sort of a piece to the output. So it's a summer. It's inverting, but it's a summing amplifier. It's doing addition. The difference one is also pretty similar. So let's label our V out. So here what we're doing is somewhat similar. Again, KCL is your friend. So if you take a look at this bottom part right here, we know that this is 0, right?
That's
right. So
if
we know that that's 0. This is a voltage divider. So I can solve for this voltage, V plus.
Oh, yeah.
Right? It's just going to be R4 divided by the sum of R3 and R4 times V2. Right. Once I know that, I know that by the second rule, that those two voltages are the same, right? I know that V minus equals V plus. So I know whatever voltage I solved for here is also there. And then KCL.
Great.
Right? This is I1 equals I feedback. Write it out, solve for it, and you'll find that in this case, there's a gain, and then you subtract out the input with this.
It almost looks like we've combined an inverting and a non-inverting amplifier.
Yeah, kind of in an odd way. Now the transfer resistance one is also pretty straightforward. This one's really easy to explain. Whatever current that you're putting in, the idea behind a transfer resistance amplifier is that you're controlling with a current. You're supplying a current, and you want your voltage output to be a function of that current times some gain. So if I know that this current is IS1 by definition, by KCL, IS1 must equal IF.
But hey, isn't that what a resistor does anyways? Converts a current to a voltage?
Well, that's why it's called trans resistance.
Ah.
So basically what you're doing is, although I wouldn't quite phrase it that way, the resistor converts a current to a voltage,
Sure.
right? I think a resistor has Ohm's law to describe it, but I see your point. And basically, if you do KCL here again, you know that this is essentially a virtual ground. You do KCL and you'll find that this current effectively just runs through here. It's ground on one side and V out on the other, and so it's pretty easy to get a voltage out of the current you're putting in, and this should really be IS1. I love all our little typos. And then transconductance is sort of the opposite direction. I have a voltage I'm putting in, and I want to use that to control a current. And there's different ways of actually building transconductance amplifiers. Here's just one of them. It's called a floating load. And what you do is you put the load that you're interested in controlling, whose current you're interested in controlling, you put it in the feedback path. And so again, golden rules help you here. You know that V plus equals V minus, which equals what?
That will equal V in this case.
Right? And so now I know what that voltage is.
It's going to be V in.
Right? And so I can go ahead and do KCL, and I can basically, it's pretty easy to show that this current here is going to be V in minus ground over whatever this resistor is. Oops, that should be 1. And this should be 1. Okay? And so once you know that that must be